Hello and welcome. My name is John Horvath. This presentation is about the coefficient of subgrade reaction, what it is and what it is not. This quote summarizes the objective of this presentation, which is to discuss a widely held but completely incorrect perception about what subgrade reaction is in general and what the coefficient of subgrade reaction is in particular. This is an outline of my presentation. I've divided it up into segments for organization and to facilitate your viewing. I'm going to start off with some background material to explain why I'm doing this presentation, then talk about what the coefficient of subgrade reaction is and isn't. I'll next move on to discussing how we got into the predicament of misunderstanding subgrade reaction and the coefficient of subgrade reaction, and more importantly, what do we do about it to improve on things. And then I will close out with some comments and acknowledgments. Well, to provide some background as to why I'm doing this presentation, this is the longitudinal and transverse profiles to a very typical building supported on a mat or raft foundation. This building happens to be the Massachusetts Institute of Technology campus in Cambridge, Massachusetts. When it was designed and constructed in the 1960s, it was referred to as the chemistry building. It's currently called the Dreyfus building, or if you look at the interactive map of the MIT campus online, it's simply labeled as Building 18. And you see it's underlain by the very classic Boston blue clay stratum and some fine-grained soils, and then ultimately bedrock. These elevations are all in feet, by the way. Now, when confronted with designing a mat-supported building in the past and in the present, very often some of the first things you hear when going to design a mat are perhaps it's called the coefficient of subgrade reaction, maybe it's called the modulus of subgrade reaction, perhaps soil spring constant or K value. You might also hear names like Winkler, Hitani, Terzaghi, Vesich. The very beginning of my professional career in the early 1970s, I was involved with the design of a mat foundation for a structure. The exact project, the details are long since forgotten, but what still is very clear in my mind is that my manager came to me one day and said, you know, we're designing this mat-supported structure. I want you to come up with the spring constant, the K value for the soil. So like Diogenes of Sinope, I looked through countless resources. I looked at various textbooks, technical publications, journal papers, things like that. And I still remember being struck at the time with the diversity of opinion of how to evaluate, how to put a number on this magical parameter called the soil spring constant or K value. And I quickly realized that this was clearly something in professional practice that there was no consensus. There was just a huge diversity of opinion. So this got me interested actually in pursuing a PhD in civil engineering, and several years later I generated a doctoral dissertation on the subject of subgrade models for mat foundations. And it was my goal in this dissertation to come up with a logical way to evaluate this parameter we call by various names, whether it's called a soil spring or K value, whatever. Well, imagine my surprise at perhaps the most significant outcome of my doctoral research was that I realized that this parameter is like the unicorn of mythology. It simply doesn't exist, or at least certainly does not exist in the way that both academicians and practitioners alike think of it. And I'm going to explain in this presentation, hopefully once and for all, why this parameter does not exist in the way that most everyone thinks of it. In more recent years, in 2020, I published a monograph on subgrade modeling and models in foundation engineering. This book, which is available, it's a softcover book. It's available worldwide, print on demand from any online bookseller. It's an extension and continuation of my doctoral research. Contains quite a bit of additional information. And also in 2020, I created a narrated PowerPoint presentation, very similar to this one, that is available on my YouTube channel. And this presentation is basically a summary and synopsis of what is in this book. So you might think, with all of this work I've done over the last 50 years or so on subgrade modeling and models, that I would have said everything there is to say about it. So you may be wondering, why am I here in 2024 talking about this subject yet again? Well, the very simple reason is that I've come to learn that these misunderstandings we have, these very widespread, near universal misunderstandings about the coefficient of subgrade reaction and subgrade modeling, or just refuse to die. They refuse to go away. Now, back in 2016, Dr. Bengt Fellenius noted that there are certain concepts in geotechnical and foundation engineering that have been around seemingly forever. Nobody quite knows where they came from, but everybody believes them to be true and correct. Nobody questions them. People may tinker with them, mend them slightly, but they just keep on getting passed down from one generation of civil engineers to the next. Academicians teach them, so the next generation of civil engineering practitioners uses them. This is now what we call a meme. Now, the meme that Fellenius was talking about is the way that we design deep foundation elements for axial compressive loads. Just about everybody believes that piles or some type of drilled element should be designed based on soil strength and the geotechnical ultimate limit state. And it turns out that's simply incorrect. In reality, it is soil stiffness and compressibility settlement as defined by the geotechnical serviceability limit state is the way that deep foundation elements should be designed for axial compressive loads. But that's a subject for another day. In my opinion, the issue of the coefficient of subgrade reaction and subgrade modeling is an even bigger meme in geotechnical and foundation engineering, simply because it's used for so many different things, in addition to mat or raft foundations. So let's begin at the beginning. Let's define exactly what is the coefficient of subgrade reaction. Now, I'm going to use a mat or raft foundation in this presentation as an exemplar application of subgrade reaction concepts. However, the things I'm going to discuss are completely general, and they apply to many other types of geostructural applications, such as slabs on grade, pavements, deep foundation elements under lateral or moment loading, and flexible earth retaining structures. Anything where soil structure interaction behavior governs design. And by the way, by soil structure interaction, I'm talking about problems where we need to satisfy both force equilibrium as well as displacement compatibility between some structural element that is bearing on or in the ground and the surrounding ground. And I want to make this definition of soil structure interaction clearer because For some reason, there are people who think that soil structure interaction only applies to earthquake loading. That's wrong. I don't know why they believe that. They're entitled to their beliefs, but it's simply incorrect. So I wanted to make that clear. I'm going to be using the geotechnical sign convention of compressive stress as positive. And I'm going to place the origin of the coordinate system at the foundation level, which is the interface between the underside of the mat and the subgrade. For simplicity and to focus on really the key behavioral issues that are relevant to this presentation, I'm going to look at only a two-dimensional behavior, and I'm going to show the upper surface of the mat flush with the ground surface. Now, that's just a simplification for the purposes of this presentation. Everything I'm going to talk about is completely general, so it applies to, you can have all the basements you want. This mat foundation could be as deep below the ground surface as you want, and it's also applicable to three-dimensional behavior. So this 2D picture is just to keep things simple so that we can focus on what I want to in this presentation. Now, if we were to analyze the complete superstructure mat subgrade system as a single entity, which, as we know, is increasingly possible to do nowadays, right? We have three-dimensional finite element software that increasingly we could analyze this as just a single problem. The primary result of geotechnical importance would typically be the total settlement W. And that's because the performance of the mat and the superstructure supported on the mat is going to be governed by differential settlements, as well as any rigid body rotation or tilt of the superstructure. As we know, with high-rise buildings, you can actually get into a situation where the tilt of the structure becomes a controlling factor. In fact, to digress a bit, there's a very slender high-rise building that was built in lower Manhattan in recent years. Was originally going to be on deep foundations, but because of the depth to bedrock, was placed on a mat foundation. I won't get into what happened, but suffice it to say that during construction, the building tilted, and it tilted several inches out of plumb. And to this day, the building remains uncompleted, unoccupied, just huge amount of ongoing litigation, finger pointing, things like this. So my point is, rigid body tilt certainly can be important for fairly tall, slender structures. In any event, of less geotechnical interest is the vertical contact or bearing stress between the mat and the subgrade. That in the context of subgrade, we refer to as subgrade reaction P. And the reason I say it's of less geotechnical interest is that mat foundations are rarely governed by bearing capacity. There might be situations where bearing capacity is a concern, but generally that is not a concern. But as we'll see, for the purposes of the present discussion, this subgrade reaction is a very important parameter. But again, this would be an outcome of this analysis. So the point I'm trying to get at here is that if we were to analyze using modern methodologies, the superstructure mat and subgrade together, two of the calculated results would be the settlement W and the subgrade reaction P. So relevant to this presentation is that at some arbitrary point I, along the mat subgrade interface, we can arbitrarily define a parameter called the coefficient of subgrade reaction, CSR. And that is simply the ratio of the subgrade reaction stress to the settlement W, and as a result has dimensions of force per length cubed. And I want to note that coefficient is the appropriate term to use here, not modulus, as some people use. The reason is simple, that in the English language, modulus in a technical context is generally restricted to material properties with dimensions of force per length squared. So we talk about Young's modulus, we talk about the shear modulus, we talk about the bulk modulus. These are material properties with dimensions of stress, force per length squared. I can't overemphasize enough that the coefficient of subgrade reaction is an arbitrary and arbitrarily defined parameter based on calculated results of the superstructure mat subgrade system. Calculated results. And I harp on that for reasons that will become obvious very, very shortly. Well, having defined what coefficient of subgrade reaction really is, let's talk about what it isn't. So additional attributes of the coefficient of subgrade reaction that are relevant to this presentation, and I've intentionally broke the problem into its three constituent parts to show you that the superstructure, of course, interacts with the mat. There has to be force and displacement compatibility between superstructure and mat in the same way there has to be between mat and subgrade. So the coefficient of subgrade reaction, as it turns out, varies from point to point along the mat and will also vary for each load case for which the superstructure is analyzed. I mean, of course, you're going to design the superstructure for a variety of load cases involving dead load, live load, wind load, perhaps seismic load, perhaps thermal load. So there are many different load case combinations you would typically evaluate for this superstructure, and each of them will provide a different distribution of coefficient of subgrade reaction along the underside of the mat. In addition, we know that coefficient of subgrade reaction is a complex application-specific function of the flexural behavior of the mat. Again, this mat cannot deform without having compatible deformation pattern with the superstructure. And the subgrade behavior is influenced largely by what we call load spreading or load transfer, and that is due to vertical shearing within the subgrade, as well as a significant stress depth that is primarily a function of the width of the foundation element, the mat in this case. I want to digress for a minute and elaborate on that last point of significant stress depth. This graphic shows the relative depth of influence, what I call the significant stress depth, capital H, that has been normalized to the foundation width B, and this shows the foundation width B in meters. Note this is log to the base 10 scale. And there are several things shown here. The black curve is the non-homogeneous elastic result. The brown curve is an empirical result that Berlin and Burbidge published back in 1985. These four colored stars are case histories that I talk about in detail in my 2020 monograph. There are two buildings at the MIT campus. One is the chemistry building or Dreyfus building that I mentioned at the beginning of this presentation. The other is a building that at the time it was built in the 1960s was called the Whittaker Laboratory. It's now called the Whittaker Building or simply Building 56. Two other case histories, Georgia State University and a bank building in Virginia. And in any event, what you see here is that this H over B relationship is highly nonlinear, okay? Very dependent on the width of the foundation. And I want to point out that anyone who's taken undergraduate soil mechanics, one of the first things you learn using homogeneous elastic theory is that the significant stress depth for a square is 2, and for an infinite strip is 4, way down here off this plot. So we see that those simplistic values of 2 and 4 that we all learned as undergraduates are simply grossly incorrect, especially when we talk about mat foundations that have more typical widths up in this range here. So to summarize, the coefficient of subgrade reaction is always a function of the load case applied to the superstructure, the flexural stiffness of the mat in this case, which is going to be influenced by load-induced cracking. All right, we all know about crack section behavior of reinforced concrete elements, as well as the time-dependent material stiffness. We all know that the modulus of Portland cement concrete is going to vary with time. Location along the mat foundation subgrade interface, load spreading due to vertical shear, and finally the significant stress depth within the subgrade. So in view of the fact that the coefficient of subgrade reaction is a very complex function of both the structural and geotechnical components of a particular application under a particular loading condition, I think we can state pretty unequivocally that the coefficient of subgrade reaction is not, has never been, and will never be a fundamental soil property. And this is despite the fact that generations of civil engineers have embraced and continue to embrace the illusionary truth that the coefficient of subgrade reaction is a fundamental soil property. So it logically follows that any and all research that has been conducted over the past many decades and still is on occasion performed in the present to determine the coefficient of subgrade reaction as a fundamental soil property is a simple waste of resources. It's a colossal waste of time and money, in my opinion. It's chasing after something that does not exist. It's like trying to find a unicorn. It simply does not exist. Never has, never will be. Well, it then is a logical question, how did we get into this predicament of thinking that the coefficient of subgrade reaction is a fundamental soil property? All right. This is the unicorn of geotechnical and foundation engineering that I would like to, hopefully in this presentation, debunk once and for all. As I said, the reason I'm still talking about this after 50 years is that I continue to see publications all the time about people chasing after the coefficient of subgrade reaction, trying to correlate it to soil properties and things like this. So how did we get in this mess? Well, very recently I published another monograph dealing with forensic engineering related to the failure of geostructural systems. And one of the things I learned is that geostructural failures typically have a causal chain, as it's called, that has several components to it. And this causal chain very often goes back in time, and that time is measured in years, decades, and certainly in some cases when we're talking about utility lines, even centuries, believe it or not. As a result, it's usually we can't identify a single unique root cause of a failure. Rather, geotechnical failures tend to be the result of some combination of events and actions that develop and evolve over time. And any one of those events would not cause the failure, but put them all together in a string, and they do. So because of this, it shouldn't be any surprise that the process of misunderstanding, misinterpreting, and misusing the coefficient of subgrade reaction, simply believing that it's a fundamental soil property when it is clearly is not, has had many contributing factors that have evolved over more than 200 years, as it turns out in this case. In addition, I'm going to show these contributing factors were originally the result, they were well-intentioned, they were a pragmatic necessity, and they were also the result of happening at a time when people had no or very little knowledge and appreciation of basic soil mechanics concepts such as vertical shearing and a significant stress depth. But the point is that while these things may have been necessary at one time, they are no longer necessary, and that ignorance about soil behavior has not existed for many decades. So it's necessary for the purpose of this presentation to trace back in time how we got to the point where we are of still believing that the coefficient of subgrade reaction is a fundamental soil property when it is not. So we got to understand how we got into the predicament we are before we can talk about, how we can correct the status quo. Well, to begin with, if we look at the coefficient of subgrade reaction, which again is a calculated result, dimensions of force per length cubed, these are somewhat non-intuitive dimensions in terms of trying to physically visualize what is this thing called the coefficient of subgrade reaction. I mean, speaking for myself, I know when I'm trying to understand a parameter in a problem, I like to visualize it. It goes a long way to helping to interpret it. The only visualization I've seen for force per length cubed is the unit weight, not the density, by the way. Some people have called it density. Of course, we know density and unit weight are not the same. It's the unit weight of a liquid. I've seen people talk about that the magical soil spring constant is the unit weight of the subgrade liquid. I don't find that particularly relevant. However, we can observe that we can take the force per length cubed dimensions and express them as force per length squared, which we immediately recognize are the dimensions of the stiffness of an axial or coil spring, force per length, per unit area, length squared, supported by that spring. So we see where this simple physical interpretation of the coefficient of subgrade reaction historically as being a soil spring, we can see where it comes from. It's simply by breaking down the dimensions of the coefficient of subgrade reaction. So we can visualize the coefficient of subgrade reaction as being a soil spring that reflects the stress displacement behavior at some point I along a foundation subgrade interface, and the notation lowercase k is the one I've seen used most commonly and universally for this spring stiffness in both research and practice. Now, back when civil engineering research and practice were based largely on closed form mathematical solutions that were solved by manual calculation, it was pragmatic to model the soil subgrade as a layer or bed of independent axial springs with the stiffness of each spring defined by K. And the reason we did this is because the interdependent structural behavior of superstructure and mat could be approximately analyzed as a unit, even in the pre-computer age, but it was still necessary to model the soil structure interaction between mat and subgrade. So if we go back to the pre-computer era, all right, as recently as the 1960s, early 1970s, for example, if you look at the American Concrete Institute design procedure for mat foundations at the time, there was an empirical relationship that said for every floor of a building, you could increase the flexural stiffness EI of the mat by a certain amount. So the point I'm getting at is that even in the pre-computer era, there was a way to approximate the superstructure mat interaction structurally simply by artificially increasing the flexural stiffness of the mat to approximately reflect the influence of the superstructure. However, it was still necessary to model the relationship between the mat and the subgrade in some way, and the alternatives available to do this in the pre-computer era were extremely limited. As it turns out, there's really only two ways to do this. Well, unfortunately ignored in this process of visualizing the subgrade as a bed of independent axial springs is the fact that these springs are not independent, but they're actually coupled to or linked together by the vertical shearing that develops within actual subgrades. And in the world of subgrade modeling, this is referred to as spring coupling. Right? So this is a term you hear all the time whenever you're talking about subgrade modeling and subgrade models. You hear the term spring coupling, and that simply refers to the natural vertical shearing that occurs within a subgrade. You push down at one point, you're going to cause a settlement at not only that point, but many adjacent points as well. That's what we're talking about here. Also ignored in this thought process that of replacing the subgrade with a bunch of independent springs is that there are several other application-specific variables, as I noted in the preceding presentation segment. All right, it depends on the load case, the flexural stiffness of the mat, the location along the mat subgrade interface, and the significant stress depth within the subgrade. So the point I'm getting at here is in the process of interpreting the coefficient of subgrade reaction, which again is a calculated result or the ratio of calculated results, in interpreting it to be an independent saw spring with stiffness K, replacing coefficient of subgrade reaction as the problem parameter, we've completely lost and ignored the correct understanding of what the coefficient of subgrade reaction is. An additional contributing factor in the thought process over many decades of ignoring the true meaning of coefficient of subgrade reaction as a calculated problem parameter was an analytical tool that emerged in the pre-computer era to model this saw structure interaction behavior between a foundation element and the underlying subgrade. And this is known as the beam unelastic foundation problem. Very unfortunate name. I've talked to many engineers and they're confused by this term beam unelastic foundation because the word elastic here is conflated very often with classical theory of elasticity solutions. In reality, the beam unelastic foundation problem has nothing to do with the theory of elasticity. The word or term elastic here simply is used colloquially and means that the subgrade underlying the beam exhibits some compressibility or elasticity, if you will. The most extensive and widely referenced and still used beam unelastic foundation problem formulation that many different solutions to different problems was a scholarly monograph that was published by Hattani in 1946. Not to detract from his work, but it should be kept in mind that Hattani's graduate education was in mechanical engineering, and his research was very theoretical in nature in the field of engineering mechanics. And he collaborated with the likes of Westergaard and Timoshenko, with Mindland and Drucker. The point I'm getting at is that I think it's fair to say that it's likely that Hattani's understanding of saw mechanics, which 1946 was still in its infancy, really. I think his understanding of saw mechanics and appreciation of saw behavior can be legitimately questioned. Hattani was a theoretician who was looking to solve theoretical problems. And my experience with people whose research is in the field of engineering mechanics is they're really interested in solving a problem for the problem's sake. Whether or not that problem and its solution relates to the real world, I think is of secondary importance to them. Central to Hattani's work was the fact the role reversal of the coefficient of subgrade reaction from being a calculated outcome to being a problem input parameter whose value is known a priori. So, as I noted previously, coefficient of subgrade reaction is calculated parameter based on calculated problem results of subgrade reaction and settlement. Hattani turned it around. He assumed that coefficient of subgrade reaction was somehow known beforehand. And he further assumed it could be modeled using the aforementioned visualization of independent axial springs of stiffness K. So we've replaced the coefficient of subgrade reaction, which is really a problem outcome, to a problem input parameter K. We should note that although Hattani did this in his 1946 publication, this was not a new idea. This linear relationship between subreaction stress P and settlement W did not originate with Hattani, but originated either with Fuss in 1801 or Winkler in 1867, depending on whether you want to believe in the Russian or German version of history. To keep everybody happy, I refer to this as the Fuss-Winkler hypothesis. I don't want to get bogged down in a discussion of which of these two researchers first proposed this relationship, this abstract relationship. But in any event, the Fuss-Winkler hypothesis, which we now know can be visualized as a bed of independent axial springs, is the simplest subgrade model that is used in research and practice. It's relevant to note that both Fuss and Winkler were active in the 19th century, many decades before modern soil mechanics came to be. So I think it's fairly clear to say that they probably did not have a good understanding of these basic elements of soil behavior in terms of vertical shearing and a significant stress depth. Now, it's important to understand that in this simple relationship, the value of K is not necessarily constant in a given application. However, there are pragmatic reasons why historically it was assumed to have a constant value in a given application. Well, as Hattani noted and illustrated in his monograph, the benefit of the Fuss-Winkler hypothesis is that it eliminates subgrade reaction P as a problem parameter by linking it to W, which is already a problem parameter. So, for example, if we take the equation of an Euler-Bernoulli or simple beam on a subgrade, this equation, we can replace P by KW. So we get rid of P as a problem parameter. Now we have a differential equation solely in the settlement W. I think people fail to realize that the simplicity of using the Fuss-Winkler hypothesis, that is assuming that the subgrade is a bed of independent axial springs, comes at an extraordinarily high price. We pay a very high price for this simplicity, simply because the end user must always select values of K that are input into an application-specific analysis. And again, I noticed that the reason for this high price, or the burden of this high price, is because we take the coefficient of subgrade reaction, which is a calculated outcome, and now we assume it's a known input parameter with a different name. And that input parameter should, in principle, consider all the key aspects of subgrade behavior that I've talked about. The load spreading due to vertical shear, plus a significant stress depth for a particular structural load case that is considered. So if you think about it, what this means in principle is that if we're going to use the Fuss-Winkler hypothesis, if we're going to use this simple subgrade spring model, we need to know the answer to the problem beforehand so that we can go ahead and calculate the correct answer. Well, as preposterous and absurd as this reality is, this hasn't stopped generations of geotechnical and foundation engineers from using and continuing to use the Fuss-Winkler hypothesis as a subgrade model in both practice and academic research. If you don't believe me, I suggest you simply go and Google subgrade reaction, Winkler, soil spring, any of those terms, and you will see constant publication to the present of people using this simplistic spring model. And I don't think they appreciate that basically it means that if they're going to do this, they better know the answer beforehand if they want to calculate the correct answer. In all fairness, this absurd reality was understandable and technologically defensible in a pre-computer era. You really didn't have too much choice other than to use this simple equation. However, this has not been technologically defensible. It has been indefensible for a very long time now, and as a result, I honestly think it's professionally indefensible. I think from a professional perspective, we're hard-pressed to continue to use something that we blatantly know is wrong, but we say, yeah, I know it's wrong, but it's so nice and simple. Well, there was a time when you could justify the simplicity because you couldn't do anything better. Nowadays, you can do better, and I think professionally, it's irresponsible not to do better. So as I've noted previously, there is no requirement in principle for this K value to have a constant value in a given application, although it was certainly almost always necessary to make this assumption in the pre-computer era, as the closed form solutions that you would find, for example, in Hatanyi's monograph, were only for the simple baseline case. But as we've known for a very long time, this assumption is inherently incorrect for even the simplest load cases. Note that in recent decades, the emergence of commercially available structural analysis software, this has, in principle, removed the dependence on closed form solutions and the use of the Fuss-Winkler hypothesis as a subgrade model. Nevertheless, people continue to use the Fuss-Winkler hypothesis. It's very attractive in both research and practice, as implementing this spring support in a structural stiffness matrix is very simple to do, as has been illustrated in countless textbooks. So in most cases, when structural analysis software is used, the assumption of K having a constant value in a given application is still made for any number of reasons, unfortunately none of which is valid anymore. So if you assume a constant value of K in structural analysis software, doing this simply allows you to calculate results more easily and elegantly and present them in many different colors. We should always remember that bad input is always going to give you a bad output. It has been noted and talked about for many, many years now that no matter how sophisticated the computer software that you may use, it will never ever make up for bad input into that program. Now, before I move on, I want to talk about a couple of specific uses, starting off with the work of Terzaghi, who summarized his thinking on the subject in a technical paper that was published in 1955. Terzaghi's paper in geotechnique is widely known and has been cited in publications to the present as a reference, but in my experience has become misinterpreted, misunderstood, and above all misused in the almost 70 years since he published it. So I want to summarize the key points in his paper. I think it's very important because they illustrate some of the things I'm talking about in this presentation. Now, there are two particular elements of Terzagh's work that I want to emphasize. And the first is that he saw the beam on elastic foundation solutions as being useful strictly and solely for structural analyses to calculate what we call local bending moments from individual loads applied to some foundation elements. So to digress a bit to illustrate what we're talking about, the assumption is that if we have a mat or slab on grade or something like this, that the true bending moments in this structural element as a result of this loading with several isolated loads can be decomposed into two parts. All right, so this overall result produces what we call local bending moments, which are simply localized flexure and bending moments isolated under each of these independent loads. This is what Terzaghi was talking about in terms of local bending moments. The assumption is that these loads are far enough from each other that each of them produces a localized effect on the structural element. In addition, we're going to have what we call global bending moments, which are the aggregate effect of all of these isolated loads, which are typically column loads in a mat foundation. All right, we know that with depth that these isolated loads are going to overlap and are going to produce a more or less uniform stress at depth. And this produces what we call global flexure, which typically has the shape of what we call dishing or sagging. Rarely do we get the upside down smile or frown type of look that we call hogging. So strictly speaking, the bending moments from these two components should be added together. Now, Terzaghi left it up to the end user to decide whether or not to separately calculate the global bending moments using some other analytical approach that he did not get into, and to combine them with the global bending moments in order to come up with a design moment diagram. And in calculating the local bending moments, Terzaghi made certain recommendations for how to evaluate the K value, the soil spring value in the Fuss-Winkler hypothesis that was constant, but he noted it was a function of several application-specific variables. Soil type, the type, thickness, and flexural stiffness of the foundation element, and the type, magnitude, and spacing of the loads that applied to the foundation element. So although Terzaghi used a constant value for K, which he had to in the pre-computer era, it was not a function of soil type alone. It was a function of other application-specific variables. Now, the other, and I think more important element of Terzaghi's work requiring emphasis relates to settlement. Very significant to note that Terzaghi left it up to the end user as to how to estimate settlements, although he stated specifically as one of his conclusions, and I quote, this quote comes directly from his paper, the theories of subgrade reaction, and meaning in this case the Fuss-Winkler hypothesis of independent axial springs, should not, I emphasize, be used for the purpose of estimating settlements or displacements. I don't know how much clearer he could have made it. Meaning that the settlements produced by a beam on elastic foundation calculation of local bending moments were never to be interpreted as quote-unquote real settlements of the foundation element. And anybody who's ever used Terzaghi's values of K in a calculation will see this, because it's very obvious that when one examines the settlement magnitudes using Terzagh's recommended values of K, they are typically an order of magnitude, not just a little bit different, by a factor of 10 at least, order of magnitude smaller than actual settlements. So stated another way, Terzagh's recommended value for the Fuss-Winkler soil springs, which I continue to see people quote and use in the present in structural analyses, were very limited in scope for use in structural calculations for local bending moments, not geotechnical calculations. They were not a all-purpose one-size-fit-all K value. Now, based on my doctoral research as well as continual research I did up to a few years ago when I published my 2020 monograph on subgrade modeling and models, one of the very rare correct applications of Terzagh's viewpoints on how to apply the beam on elastic foundation concept, that is for local bending moments only, was published in an ASE seminal 1972 paper by D. Simone and Gould of Muser-Rutledge, now MRCE engineers. It's really, I have to say, in my opinion, one of the genius papers that correctly understands what the beam on elastic foundation is useful for. As it turns out, D. Simone and Gould and their firm were involved in the design of the two mat foundations on the MIT campus. The buildings I've mentioned previously, the chemistry or Dreyfus building and the Whitaker Laboratory building. Both of these were designed and built in the 1960s, and very interestingly, settlements were monitored for several years after construction. So these two mat foundations are really quite excellent because they provide not only construction details, but several years of post-construction observed settlements. So it's really, this is an excellent paper for, if you're going to write a paper about comparing your calculations to observed settlements for a mat, as I've done, these are great case histories to use. In any event, D. Simone and Gould correctly point out that they only used the beam on elastic foundation concepts for calculating bending moments, design bending moments in the mat foundations. They used other methods for calculating settlements of the mat foundations. Now it turns out their settlement calculations were a bit off. The mats settled about twice as much as they calculated. Nevertheless, these two buildings still exist roughly 60 years later, and as best as I can tell, they're still functioning properly. So even though these buildings settled more than was anticipated, apparently that has not inhibited their performance. And to the best of my knowledge, there has been no problem with the structural behavior of the mat foundations. I'd like to discuss one more body of work that echoes Terzagh's work and conclusions with respect to subgrade reaction from a different perspective. And this is the research outcomes of the late Professor Vesage and his colleagues at Duke University. Vesage's research in the 1960s that culminated in a 1970 research report that was sponsored by the Highway Research Board in the United States, now known as the Transportation Research Board, focused on what we call rigid pavements, that is pavements of Portland cement concrete, generally reinforced Portland cement concrete. Now, Vesage and his colleagues had access to a large amount of data that were obtained on full-scale pavements that were installed and tested in the late 1950s as part of a multi-year American Association of State Highway Officials, now AASHTO, road test program in Ottawa, Illinois, that had concluded in the early 1960s. So Vesage and his students had a tremendous body of work so they could compare actual load settlement behavior to various theoretical models that they investigated. Now, the conclusion of Vesage's 1970 report that is relevant to this presentation is that for a Fuss-Winkler subgrade model of independent axial springs with a constant K value, that you could match the bending moments in a rigid pavement to a K value, or you could match the settlement profile to a K value, but never with the same value of K. So if you wanted to state it another way, if you wanted to match bending moments and settlements, you had to use different K values. Well, clearly, if this K is a fundamental solid property, it's fundamentally impossible to have to use two different values to get correct results. So this was another way of pointing out that the Fuss-Winkler hypothesis or subgrade model of independent axial springs with a constant magnitude K value is not a fundamental solid property. It's not a valid solid model because you can't match both moments and settlements with the same K value. And it should be kept in mind this was even for the simplest of applied loadings. This was for a single concentrated point load on the surface of a rigid pavement. So you couldn't get any simpler than this. You have just a single isolated point load, and even then you could not come up with a unique K value that would give you both correct moments and settlements. So as I said, the logical conclusion is even for the simplest loading, the Fuss-Winkler hypothesis with a constant magnitude K value for the springs cannot adequately forecast both moments and settlements at the same time. So to sum things up, the transition of the coefficient of subgrade reaction from being an arbitrary expression of calculated outcomes, as it is in reality, to being an independent spring whose stiffness K is an input parameter and thus must always be known beforehand, was born largely out of pragmatic necessity in a pre-computer era of closed-form solutions to theoretical problems that were based on highly simplified physical models that had to be solved by hand calculation using a slide rule. And I can tell you out of first-hand experience, having lived through the transition from the slide rule era to the computer era, that I know what it's like to have to deal with these closed-form solutions when all you have is a piece of paper and a pencil and a slide rule. In several cases early on, it was also a time frame, again, in the 19th century, early 20th century, when modern solid mechanics either had not yet developed or was in its infancy. So I think there was no appreciation of relevant solid behavior such as load spreading via shear or a significant stress depth. Really, one can't fault these early researchers about not knowing about something which simply was not known at the time. And I think this is reflected in the work of Fuss and Winkler in the 19th century and Tanya in the early 20th century, when for one reason or another, either these researchers had no knowledge or little understanding and appreciation of actual solid behavior. So even when those who were knowledgeable about solid mechanics came along, Terzaghi in the 1950s, Vesage in the 1960s, they were still hobbled by the limited, at least by today's metrics, computational capabilities of the era. They had to work with closed-form solutions, hand calculations, and a slide rule. It should be kept in mind that in the pre-computer era that spans the work of Fuss in 1801 to Vesage in the 1960s, the primary goal of all of these researchers at the time was to model the structural flexibility of mat foundation and other types of geostructural elements such as rigid pavements, slabs on grade, in order to more accurately estimate bending moments in this geostructural element that was bearing in the ground. It's important to remember that at the time there was only one other alternative, and that was to use the so-called rigid method that we still use to the present with footing foundations, where we assume that the subgrade reaction is a trapezoidal distribution whose distribution is based solely on static equilibrium and the simplistic P over A plus minus on MC on I formula. So the point I'm getting at is that we need to be fair to understand why things were done in the past. In the pre-computer era, you basically had two ways to model, say, a mat foundation. You could assume it was rigid, and at one time, American Concrete Institute said this was a valid way to design mat foundations. You could assume it was rigid and use this footing type approach, or if you wanted to be a little bit more elegant with things, you could use the beam on elastic foundation solutions. But again, this was for structural behavior. The whole idea was to get because in most cases the rigid method tends to give you, in a mat foundation, tends to give you bending moments that are way too large. So if you want to get a more accurate estimate of bending moments, considering the flexibility of the foundation element, the only game in town was the beam on elastic foundation solutions with a constant K value. Again, notice that these were really for a structural purpose. It was not supposed to be used for estimating settlements. And again, the fact that the simple soil spring subgrade model was always structural in nature, never geotechnical in nature, was a central tenet of Terzagh's 1955 paper. And I think Terzaghi made it crystal clear. It's worth repeating again, this is a quote directly from his paper. The theories of subgrade reaction, that is, using the independent soil spring model with constant values of K, should not be used for the purpose of estimating settlements or displacement. So to wrap things up, unfortunately, and this is why still 50 years later I'm still preaching about this, design professionals in practice, as well as instructors and research and academia, I think even in the present have collectively failed to realize that the ship of necessity that once made us use the Fuss-Winkler hypothesis and its soil spring concept, that ship sailed a long time ago when the digital computers arrived in the 1970s and beyond. Thus, this hoary chestnut that the soil spring constant is a fundamental soil property that people continue to believe in to the present, I think really bogs down civil engineers with a lot of old baggage. We're using concepts that predate modern soil mechanics and modern computational tools, and we continue to hand down this meme of that the K value is correlatable to fundamental soil properties from one generation of civil engineers to the next. And I say this from one who was involved in academia for over 30 years. We continue to see professors who teach their students that the K value this is the way to go, and it's a fundamental soil property. Well, it's no surprise that these students are going to go out into the real world, and they're going to use these ideas that should have been abandoned decades ago. I don't know why we do this, because I'm going to show you in the following segment the theoretical tools to give us a better subgrade model than the Fuss-Winkler hypothesis date back to at least 1940. So the logical question is, how do we as a profession once and for all get rid of these old-fashioned ideas that were a necessity in the pre-computer era. These ideas are decades too old. So let's move on to the next segment about what do we do about this predicament that we're in believing about a soil spring constant being a fundamental soil property. How do we move on from this unicorn of geotechnical and foundation engineering? What do we do about it? How do we fix the problem? I think it all goes back to a mistake that is often made in both research and practice, is the failure to realize that calculation tools are not fixed in time. This quote comes from a proceedings of a symposium on mat foundations from about 20 years ago. And Hemsley correctly noted that certainly these old ideas in the past, the use of the Fuss-Winkler hypothesis of independent axial springs with a constant K value, that there were designs that had success. We can't deny that. And certainly, if we look at those two buildings I mentioned on the MIT campus that were designed based on those old-fashioned concepts, by all appearances now 60 or so years later are still performing well. However, the fact that we're able to use these concepts in the past successfully does not mean we should continue to use them. And they're really unacceptable in modern practice. So I included this quote to show you that I'm not the only one saying, look, fine, this is what we did in the past when we had nothing better. We have something better. That doesn't justify doing what we did in the past any longer. I think it's very reasonable to say that we should not be using 19th century subgrade models based on 20th century closed form solutions and a slide rule when we have 21st century numerical tools available to us. We, of course, should have moved on decades ago. We haven't, but at least if we move on now is better than never. As some guidance on how to do this, I'm going to modify a quote from Einstein. Basically, make things as simple as necessary, but no simpler. And it turns out that in the world of subgrade models, there are two methodologies, two schools of thought for doing this. One school is the simplified continuum concept. And I suspect this school of thought is not known to most civil engineers. It's a concept that I attribute to Eric Reisner in the mid-20th century, in the 1950s. And basically, the simplified continuum concept and the subgrade models that evolve from it say that if we start with an elastic layer, homogeneous isotropic elastic layer of finite thickness H, and we make simplifying assumptions to the various governing equations for that elastic layer, we can wind up with a simplified subgrade model. The other approach, which is more familiar, I think, to civil engineers, is the mechanical subgrade approach. In the 1960s, Kerr and Rhine showed that we can go through a process of building subgrade models by adding various mechanical elements, such as a shear-only layer, a tension membrane that produces shear effects, flexure-only layer, additional spring layers, to the basic Fuss-Winkler spring model of just a layer of independent springs. So in the mechanical approach, we start simple and we build more complex. And you could show that in the limit, an infinite number of mechanical layers would be a theoretically exact solution. And we see that at some point, And these are just the names of some researchers who have pursued this research and what their models look like. We see that at some point the solutions become non-unique, meaning that different combinations of mechanical elements produce the same effect. So essentially what I'm saying is that with these two approaches, the simplified continuum approach, we start exact and then we make things simpler. In the mechanical approach, we start simpler and make things more complex. But no matter how we approach the problem, the methodologies have the same end result that they're after. The goal is to come up with a subgrade model that strikes a balance between theoretical rigor and ease of use, that above all else includes inherently spring coupling. Because research has shown that the single biggest shortcoming or deficiency of the Fuss-Winkler hypothesis, that is a bed of independent axial springs, is the lack of spring coupling. That is some tying together of the springs. Because that's from a perspective of subgrade reaction, the single most important thing that we want to replicate is that when we push down on the subgrade at some point, we get settlement not just at that point, but at adjacent points as well. So spring coupling is the most important thing we have to incorporate in a subgrade model. It's the single most important thing that the Fuss-Winkler spring hypothesis lacks. Now, both the simplified continuum and mechanical methodologies for producing subgrade models result in what are called multiple parameter or multi-parameter subgrade models. That is, they model the subgrade effects using more than the single parameter, a layer of uncoupled springs, of the baseline Fuss-Winkler hypothesis. So basically, we add terms to both sides of this equation. Now, it turns out multi-parameter subgrade models have appeared in the published literature at least as early as 1940, so they've been around the better part of a century. However, such models never gain traction, and I can tell you this from personal experience. I mean, I published my doctoral dissertation with a multi-parameter subgrade model in 1979, and I stepped back and I waited for the world to embrace it. And all I got was a big yawn. So it took me a while to realize that simply having a multi-parameter model was not enough for academicians and design practitioners to embrace it. All right? There's been a reason that multi-parameter has been around for a long time, but they're not much used in research or practice. And it's simply because both the simplified continuum and mechanical approaches to subgrade modeling have pros and cons that inhibit their use. For example, with mechanical models, on the plus side, on the pro side, the model components, right, springs, shear layers, tension membranes, these are things that we can easily visualize. And we can actually model them pretty easily in commercially available structural analysis software nowadays. It's no big deal to model them. The problem comes in is, okay, you've created this model. Tell me what the spring constant is. Tell me what the tension is in the membrane. Tell me what the shear modulus is in the shear layer. It's how to quantify the different equation coefficients. This is the downside or con to mechanical models. Now, if we look at simplified continuum models, their negative or con side is the fact that modeling an elastic layer with simplified behavior in structural analysis software is not straightforward. On the plus side, the coefficients in a multi-parameter model developed by the simplified continuum technique, it's fairly straightforward to come up with the values from problem geometry and fundamental solve properties from state of practice site characterization. So the point I'm getting at here is that some time ago I realized that the reason that people were not embracing multi-parameters to finally replace the Fuss-Winkler hypothesis of a layer of independent axial springs is that whether you used a mechanical model or a simplified continuum model, they both had pros and cons, and it was the cons that were inhibiting people. Well, the solution that I evolved in the last couple decades, and I have to credit my collaboration with Regis Colasanti, PE. He's been my collaborator with me in recent decades, is to come up with what we call a hybrid subgrade model. And this is to simply cherry pick to combine the best elements of the simplified continuum mechanical subgrade models in order to produce a user-friendly subgrade model. So the hybrid subgrade model approach uses the pros from both of these, and we eliminate the cons from both of these. So it's the best of both worlds. So the rise of the simplified continuum model, for example, here's the differential equation governing this model. We can come up with the necessary properties, Young's modulus, shear modulus, things like that, from site characterization. There are ways to come up with the fictitious thickness, H, of this elastic layer. I'm not going to go into them here. I go into that in great detail in my monograph on subgrade modeling. In fact, I lead you through it step by step. And if we look at the Horvath-Colasanti mechanical subgrade model, here's the differential equation. It's basically two layers of springs sandwiching a tension membrane, and it's this tension membrane that is providing the necessary shear coupling. This model is very easy to implement in structural analysis software. I've co-authored some papers with Mr. Colasanti that we've published in ASCE journals. I also talk about it in my 2020 monograph. This is very, very easy to implement in whatever structural analysis software you use. Colasanti happened to use ANSYS simply because that was the software that he had available to him in his firm, but any modern structural analysis software, very, very easy to implement this model. So the way you use this in practice is simply you combine these two models into a hybrid model. So we program the mechanical model in the structural software, and then we come up with the spring constants and things like that. We can relate them to solve properties and problem parameters using the elastic continuum model. And we've applied this. This is not just a research idea. We've applied this to 4 case histories, the 2 buildings on the MIT campus, building on the Georgia State University campus, and a bank building in Virginia. So we've actually used this in practice to 4 mat foundations where there have been measured settlements, and our calculated results compare very favorably with the measured results. So again, I'm not going to go through this in detail here because I've done that in other places. If you look at my 2020 monograph, I show you step by step for each of these case histories how you could, just using everyday site characterization that we have in practice, you can come up with results. So again, I want to strongly emphasize these are not just some research ideas, that this is a very this hybrid subgrade model is very usable in routine practice. It requires nothing more than the site characterization that every geotechnical engineer uses nowadays, and it requires structural analysis software that every structural engineer uses nowadays. So this is a very practical to use subgrade model. There is no reason why this subgrade model cannot be used in research and practice right away. And again, we've illustrated this with several case histories where I show you step by step how to use the model, then compare the calculated results to measured results with good agreement. So to wrap things up with some closing comments, there are many foundation applications, such as a mat-supported building, as I've used in this presentation, where soil structure interaction modeling is a must. That is, we have to consider both force equilibrium and displacement compatibility between a structural element and the ground in contact with it, if accurate analysis of the overall structure subgrade system is to be obtained. Now, although there have been tremendous advances in computer hardware and software in recent decades, a rigorous three-dimensional numerical modeling of a combined structural and geotechnical components of many soil structure interaction applications is simply not practical as a sole or even primary analytical tool to use in routine design practice. What I'm saying here is, yeah, we can do a lot of tremendous things with three-dimensional finite element software, but in a lot of cases for these very complex models, it may take hours, perhaps even days for an analysis to run. And when you're going through design process, when you're looking at different design alternatives, different loadings, things like that, you need a simpler tool to use during those intermediate steps. Now, you very well may analyze the final design with the exact software, but you need something simpler during the design process. So that's where subgrade modeling has come in. The point I'm getting at here is, even with the current capabilities of three-dimensional finite element software, there still is a need for subgrade models in practice that strike a balance between theoretical rigor and ease of use for analyzing soil structure interaction applications. So this requires a subgrade model that is computationally efficient, yet reasonably accurate. You have to use a subgrade model that inherently captures the essential components of actual subgrade behavior, which, as I said, I can tell you from experience, is you need to inherently model the load spreading via shear, the spring coupling, and the effective stress depth without having to resort to guesswork or gimmicks or making excessive theoretical compromises, such as inherent with the Fuss-Winkler hypothesis that lacks spring coupling. All right? There's no reason in this day and age, you should have to guess at the final answer so you can come up with a K value to calculate the final answer. By using this hybrid subgrade modeling approach I mentioned previously, there's no guesswork involved. You go through a conventional site characterization process. You come up with the model parameters that inherently build the spring coupling and the significant stress depth into the model parameters. You put them in a structural analysis software. There is no guesswork anymore. The coefficient of subgrade reaction is back to where it always began and always belongs. It is a calculated outcome. It is not an input parameter. So this Horvath, Colasanti, Reisner hybrid model, we've proven it. Again, this is not just a research concept. We've used it on actual case histories to show that it's a very practical subgrade model to use. It strikes that sweet spot, that optimum balance between theoretical rigor and ease of use. I think Colasanti and I have shown that there is absolutely no justification anymore in either practice or research for using the Fuss-Winkler hypothesis as a subgrade model, where you have to come up with K values, you have to guess at the right answer, and then cross your fingers and hope you calculate the right answer. Again, I can't emphasize too much that the inability of the Fuss-Winkler hypothesis, the independent axial spring model, to inherently account for load spreading due to vertical shearing, as well as to rationally account for the significant stress depth that occurs in actual applications, places the entire burden on you, the end user, to estimate these effects a priori so that they're in the K values that you input across the entire foundation subgrade interface. And again, if you're going to use the Fuss-Winkler spring model, you have to know that you need to know the correct answer to a problem beforehand so that you input the correct parameters in order to calculate the correct answer. So the inherent inability of the Fuss-Winkler hypothesis to capture fundamental soil behavior has resulted in generations of geotechnical and foundation engineers wasting time and money looking for what is presumed to be a fundamental soil property that in reality does not exist. Right? This mythical soil spring constant K is, in my opinion, the biggest unicorn and meme in all of geotechnical and foundation engineering. I've said it before, I can't say it enough. This K parameter is not, has never been, and will never be a fundamental soil property. And if you don't want to believe me, maybe you'll believe Terzaghi. He made this clear almost 70 years ago. With that, I'd like to finish up with some acknowledgments. I can't say enough about the research and collaboration and contributions of Mr. Regis Colasanti, PE, to the advancement of subgrade modeling and models in recent decades. I acknowledge him with substantial gratitude. In particular, the Horvath-Colasanti mechanical subgrade model and its implementation in commercially available structural analysis software as part of the Horvath-Colasanti-Reisner hybrid subgrade model would not have been possible without his seminal mission-critical contributions. I say this with all honesty. When I finished my doctoral dissertation in 1979, trying to be objective about it, I said, well, you know, I think it's a nice piece of research, but I was unsatisfied. And the reason I was unsatisfied is with the state of knowledge at the time, I was missing that critical link to be able to say, fine, I came up with this great idea of a simplified continuum model. How do we implement it in actual practice? And that missing link was how to incorporate it into structural analysis software. It took longer than I would have wanted, but I'm very fortunate that eventually, with the assistance of Mr. Colasanti, we were able to come up with a way to implement this subgrade model in commercially available structural software. All right, we came up with a practical way to turn theory into practice. I want to point out that Colasanti's own published work, including his own independent assessment of a mat foundation case history involving the first American bank building in Tyson's Corner, Virginia. This was a case history that Dr. Paul Main, recently of Georgia Tech, published some years ago, and was reanalyzed by Mr. Colasanti and I. I published an assessment of it in my 2020 monograph, and Mr. Colasanti has his own assessment using a program G183 that he wrote. G183 is Colasanti's own original subgrade modeling program. So both his works as well as his program can be found in ResearchGate under his name, and So I highly recommend that if you want to look at Mr. Colasanti's work, you could find it. He's kindly made it available for free access and downloading at ResearchGate, and here's the URL for his ResearchGate profile. So with that, I want to say thank you for your interest and attention. If I have any hope out of this, is that hopefully once and for all I've convinced at least some of you to at long last give up your quest for relating the spring constant, the K value, to soil properties. That relationship does not exist, never has existed, never will exist. The way forward is to embrace, I think, these hybrid subgrade models that rely on nothing more than ordinary site characterization and ordinary structural analysis software. You don't need any special proprietary software. Every civil engineer out there could do it on his or her own effort to do your own site characterization, use your own structural analysis software, and you too can have results that are fundamentally and inherently better than the way we've been doing things for far too long. So with that, again, thank you very much, and I want to wrap this up.